Hey, Algebra 2 friends. We are here in Chapter 9. We're at the end of the chapter. It's Section 9.6. We're going to be talking about solving rational equations and inequalities. So here's our vocabulary. We only have two terms we need to know about, which is what is a rational equation and what's a rational inequality. So let's get started. A rational equation is going to look like this. It will basically be an equation where you have rational expressions occupying parts of the equation. So basically what we've been working with before, the rational expressions, but with an equal sign, all right? And we'll be expected to figure out what x is. What's a rational inequality? Glad you asked. Well, it's a lot like a rational equation, except we have an inequality symbol where the equal sign should go. And so the big deal that we're going to be dealing with is how to solve these things. So let's get started. To solve a rational equation like this one in example 1, it is a lot like what we would do usually. We kind of want to have a common denominator. Not kind of, we do. We need to work with a common denominator. So since we've got these three terms, like if we only had two terms, real quick, if we only had two terms, let me just pretend this term doesn't exist. This is a rational equation, but I would cross multiply this, right? I'd go 3 times 4 is equal to 3 times z plus 2 and do what I gotta do. But since I've got these three terms, I'm definitely going to look for a common denominator. So what would that be? If you remember earlier in the chapter, I would always say, hey, we need to make sure all of the denominators are the same and each denominator needs to be contained in my new denominator. So I'm just putting 28 with all of these, which is 4 times 7, 4 times 7, 4 times 7. So 28 is represented here. Z plus 2 needs to be represented as well. And so I'm just going to throw that in there. And where if I put it in, let me make that look more like a Z. If I throw that there, I've got to throw it around everywhere. And then 4 needs to be represented. But I think you guys already see there is a 4 in my denominator. Therefore, every denominator is represented, and I've come up with the least common denominator. Now that I've done that, let us adjust the numerators for what we've added into or multiplied into our denominator. So we have 9 times z plus 2. If that's not making sense, we do need to have a chit chat a little bit. This one is going to be 3 times 4 times 7, or 3 times 28. And over here, what was not in the denominator before was the 7 in the z plus 2. So this is going to be 3 times 7 times z plus 2. I'm getting my 7's and my z's confused. I'm going to do it like that to keep it consistent, all right? And then so now, here's the thing. When I was a kid, I would look at this and go, okay, now that the denominator is the same, I really just need to work with my numerator. Think about it. If I told you 1 over a plus 2 over a is equal to something over a, you know that since we're dealing with a common denominator, you don't really need to worry about that. You're just adding the numerator and you're just concerned about the top. And that's pretty much the same idea here. So I'm going to put a wavy line, a highlighted wavy line, kind of eliminating this from our attention, okay? I'm not totally crossing it out because we do want to think about the denominator in some way. So watch how this folds out. Now we have this new equation, which is going to be 9 times z plus 2 plus, now what does all this multiplied give me? 21 times 4, I think, is 84. 84 is equal to, now we've got 21 and we're going to distribute it through there. So that's going to be 21 times z plus 2. And then what we're going to do is just do what we're supposed to do. 9z, solve it like we know how to solve it, plus 84 is equal to 21z plus 42. And with a little bit of basic algebra 1, we get ourselves back to the idea that z is equal to 5. Now, the reason why I didn't cross this out is because I am ignoring it, but I'm ignoring it kind of sort of. I need to make sure that there's no problem with my answer and my denominator. You got it. I don't want to get an excluded answer from my denominator, and I don't, because you notice that 5 plugged in does not cause my denominator to be 0. So I feel like this answer is good. You definitely could check it by plugging it back into the equation, making sure everything's legit. But since I see that I'm not getting a 0 in the denominator, I know I didn't come out with some Crazy answer, z is equal to 5, and I'm stopping there. So let's get right into this one. We're going to set up so that we have a new denominator, and you guys can see that whenever we're doing a problem like this, we want to see what our denominator is made of. And hopefully you guys can see that my common denominator will be this denominator, r minus 1 times r plus 1, because this denominator is just 1. So I'm going to write that all across here. And now it's time for us to readjust the numerator. So over here, the numerator only had an r in it, and it only had a 1 in the denominator, meaning it needs everything. So I need to put everything in my denominator into my numerator. So this is going to be r times r minus 1 times r plus 1. And then here, this denominator already had everything that, I didn't change the denominator, therefore I won't change my numerator. That was easier said. And then now over here, I see that r minus 1 has been added to the denominator, but I actually didn't factor this, so I'm going to factor this right now. So I'm just factoring what's there. This should be r, let's see, r, I don't know, can this be factored? It doesn't look like it. Oh, nuts. I wish it would be able to be factored, but that's okay. So this is r squared plus r plus 2 times r minus 1, and don't cancel out because remember we wanted the common denominator so we can join everything together. I'm going to do my wavy hazy line where I'm kind of ignoring this but not necessarily eliminating it. So ignoring the denominator, this is what I'm seeing as my equation with just the numerators. And of course, I'm going to have to FOIL this out or multiply all this together, extended distributive property here too, and then simplify. So I'm going to do that without you guys having to watch me do that. So after that, we're going to join some like terms together. Nothing over here looks like we can join it together. I'm just going to reorganize it real quick just for nerdy sake, I guess. All right, so I have it in descending order. Let's do the same thing over here. But first, we've got these guys are alike and they cancel each other out. And then these guys can come together to give me one r. So I end up with r cubed plus r minus 2. Pause and take a look at it if it's not making sense. All right, at this point, I'm looking at both sides. And if I were to subtract 3r cubed, rather, from both sides, they would cancel each other out. So then finally, I have r squared minus r minus 5 equals r minus 2. How do we solve this? Well, this is a quadratic. So I'm going to put an arrow up here. I know you guys are like, she's so sloppy, but stay with me. R squared, I'm going to move everything over to one side because that's what we do when we solve quadratics. And we set it equal to 0. Yeah. Okay, you remember it. All right, so now r squared minus 2r minus 3 equals 0. We're going to see if we can factor it. If not, we're going to pull out the quadratic formula. But I think we can factor this. Negative 3, it can be, we can get that from minus 3 times a positive 1. So that's r minus 3, r plus 1. That looks good. And then we see that our zeros would be r is equal to 3 and r is equal to negative 1. And you know what we do? We've got to check our answer. And the real place of concern is that denominator. We want to see if any of these will make our denominator 0. And we see we do have one. This answer cannot work. The reason why, I plug it in, I get a 0 in the denominator, and you know that's bad news. So our answer will be r equals 3 as we eliminate r equals negative 1 because it'll cause a problem in our denominator. Here we have a work problem which fits underneath the idea of rational equations. And I think we've talked about them before. Work problems are kind of like problems unto themselves. So let's kind of talk about this one. I would like us probably to do more examples in class together if we get a chance. So don't be opposed to doing more. Okay, so here's the deal. What we're talking about are tunnels. The channel is a tunnel under the English Channel. That's a whole lot. That connects England with France. It is 32 miles long with 23 miles of the tunnel underwater. All right, so when building the channel, the English and the French each started drilling on opposite sides of the English Channel. The two sections became one in 1990. The French used more advanced drilling machinery than the English. Suppose the English could drill the channel by themselves in 6.2 years, and the French could drill it in 5.8 years. How long would it have taken the two countries to drill the tunnel? All right, so this is a classic work problem. You've got one person with one rate, usually an hourly rate, and another person with another rate, usually an hourly rate, and you're trying to figure out how long it's going to take them to finish the job. So here, let's consider this. So the first thing I'm going to define is the variable x as the number of years that we would be working. So if we think about that, if I don't know, if England worked for 6.2 years, how much of the job would be done? So if I did 6.2 divided by 6.2, I'd have one job done. But England worked for X amount of years in this scenario. So we don't know how long it's going to take for the one job to be done, but we know if it were just England alone, it would be 6.2. But since the French is a part of it and they're working at exactly the same time, we need to consider what they would add to the job, also still just looking for one job done. Does that kind of make sense? I know it's a little bit weird, but if you haven't seen it before, it will feel weird until you practice some more. So we're going to use x divided by 5.8 plus x divided by 6.2 equals 1 as our equation, where x refers to the number of years these two groups would be working together to get one job done. All right, so with that, what we need is a common denominator. So this isn't the least common denominator, but I'm just going to throw out a common denominator of multiplying both of these guys together because, divided by 0.2 and all this stuff, I think I'm just going to do that. So when I multiply them together, I get 35.96 as the product of 5.8 and 6.2. So that'll be my common denominator for this equation, 35.96. And that's equal to, again, 35.96. We want all of the denominators to be the same. And so knowing that I multiply these two together, you know that the numerator will basically need to be multiplied by 6.2. So that's 6.2x. This numerator will need to be multiplied by 5.8. And this numerator would need to be multiplied by 35.96. And so now, there's an x there. All right. And so now we can we can ignore the denominator out here because there's no x value down there. And now here's our new equation. Okay, 6.2x plus 5.8x is equal to 35.96. Adding these guys together, we're going to end up with a 12x is equal to 35.96. And we need to divide both sides by 12. And you can see 35.96 is mad close to 36, like super close. And so you can see x is going to equal approximately 3 years. I could probably do 2.97 years, but it's going to be approximately 3 years when I divide that 12 into this number that's super close to 36. So that's how you'd handle one of those problems. Let's see if we got time for another problem. This problem we could probably shove in the last couple of minutes, but then we have another one. I think we're going to just do a part 2. I know nobody wants part 2, but we're going to do it anyway to finish off our lesson. So let's go ahead and check out, finish this up in part 2.